Hi, everyone. I'm Skyler Thomas, and this is Taming State and Data Challenges for Machine Learning Applications in Kubeflow. I am the lead architect for HPE Ezmeral Data Fabric and the HPE Ezmeral MLOps Kubeflow support. Now, these products can really help with a lot of the things that we're going to be talking about today, but I'm not going to actually talk about the product's capabilities. I'm going to talk specifically about the challenges in a vanilla environment and how to solve those without special products. If you're interested and you think some of the ways to solve things on bare metal are a little difficult, then I'll have links at the end of the presentation and you can check them out if you're interested. But today I'm really hoping to accomplish several things. First, I want to discuss the challenges that occur when you mix data scientists working on machine learning and AI with IT operations. Next, I want to give a brief overview of Kubeflow workflows for people who may not be super familiar with how machine learning works in Kubernetes. And then I'm going to talk a little bit about the various state and data challenges that Kubernetes has and therefore Kubeflow applications have. Finally, I'm going to dive a bit deeper into very specific challenges, talk about different tips on how to handle them when you run into them. This is a very short presentation, so we're not going to dive super deep. There's a lot to discuss in this area, but hopefully we'll have time to answer some of your questions after we present. And at the end of the session, I really hope you leave it more prepared to face the challenges that you're going to see with state and data in Kubeflow and have some tips in your back pocket to solve them. I'm sorry we're not together in person today. That would have been amazing to sit down and bounce things off of each other at a conference. But hopefully we accomplish a lot, and maybe we'll see each other at the next KubeCon. Let's talk a little bit about data scientists versus IT. If you think about both groups, they have kind of antithetical goals. What each group wants is almost the polar opposite of what the other group wants. Data scientists want really custom hardware, high memory GPUs, TPUs. IT really wants cookie cutter commodity machines wherever possible. Data scientists want all the hardware they can get, and IT really wants to encourage efficiency and sharing. IT wants to standardize applications and reduce license costs. Data science really wants to use a variety of applications and frameworks. IT wants software that's safe and supported. Data science wants cutting edge tools from academia. Finally, IT wants to carefully categorize and restrict data for security and regulatory reasons. Data science really wants to use all it can to train their models. There's really been no good way to solve these problems except to isolate data science's environment. Basically, the organization backs a truck up with a lot of money and other resources and creates an entirely separate environment with all the bells and whistles that data science wants. And in certain use cases, this is efficient. Other use cases, it's simply not sustainable for data scientists. As we have more and more data science going on in organizations, it becomes less sustainable. Basically, every environment has to be hand rolled. The cloud can help a little bit here, but there are challenges with GPUs and TPUs in the cloud too. So there's no perfect answer in the traditional way of doing things. Kubernetes can help us a lot. But before we think about Kubernetes, let's take a step back and look at how we were doing some of these data science and big data tasks before Kubernetes. We're using things like Spark, TensorFlow, and Hadoop, and we learned a lot of things from those environments. And the biggest thing we learned is hand-rolled environments are incredibly expensive. That really brings us to Kubernetes and why Kubernetes is so exciting for machine learning and AI tools. Kubernetes solves several critical problems with these traditional machine learning and big data environments. First, hardware doesn't need to be dedicated to data science. We can use that hardware for other workloads when a training job is not running. or we can rather train when the hardware is not needed for other purposes. That tends to be the way we look at it. Complex scheduling allows different types of nodes to be used. So IT can have a lot of nodes that are normal, and data science can have their GPU, TPU, high mem nodes. App containerization means many more types of apps can be supported. But Kubernetes has a number of challenges, even though it solves a lot of problems in the data science world. The key to all of this is the name data science. The data in that name is the clue. Machine learning requires a ton of data or state to work. And Kubernetes was really initially designed for stateless apps. Over time, handling state and applications has improved in Kubernetes. We now have things like persistent volumes and storage classes, CSI, volume-based scheduling, and others, but there's still major challenges. So, what is all of the state that we have to think about for machine learning applications? Well, there are dozens of different types, but I'd like to focus today on really 5 of the key ones. The first type are notebooks, and notebooks present a challenge in that different data scientists want to share their notebooks with other users, and there's a tendency to want to embed a notebook in a container and create this link between a single container and a single notebook. But in cases where it makes sense, where users change some things and they want to share that data, you really need to think about how to handle notebooks. Training data is probably the key type of data. We work with customers doing self-driving cars that have sensor data that's multiple hundreds of petabytes. This presents a raft of challenges. Some of the questions you really have to ask about training data are: how do we move this data close to compute? Or how do we move compute rather close to the data? Because it's very hard to move the data around. How do we protect privacy if some of this data is sensitive? How do we follow legal requirements? Libraries are yet another area. If you have a container and it's running a Spark job or TensorFlow job, there are going to be certain compute libraries that you need. Do you want to have to create a container every single time you need a new library? Do your data scientists have to be experts in the containers? That's a challenge. Models. How do we query and promote model files into production? Logs. All of these applications are generating massive amounts of logs. Many of these logs are critical for the data scientists to be able to look at to make modifications to their training jobs. How do you handle those things? All of those types of state are challenging. Okay, so we've talked a little bit about the problem space and the challenges we face and the types of state that we're interested in, but let's make sure and review the actual data science workflow that most people go through. If you're not familiar with it, most vendors give workflows that are many steps long. I've kind of simplified things here into 4 steps. Really, you capture some data. This can be really challenging. I'm not going to address it very much in today's presentation, but you need to deal with things like streaming. You need to do data cleansing. There are all kinds of challenges with capturing the data and making sure the data is okay. That kind of bleeds in a little bit of a gray way into exploration. This is the work that a data scientist does within a notebook, experimenting, looking at data, trying to think about it, try different regressions on the data, try very simplified toy models with the data. Then they move on to training it in a distributed fashion across all of these nodes in our Kubernetes environment. And finally, they serve a model that was created during training. A lot of data science is automating these steps so you can do it over and over and over again, but that's really kind of the gist of things. As I mentioned, notebooks are really the heart of the user experience that a data scientist has in the Kubernetes environment with Kubeflow. Notebooks are really what these data scientists work with. They're container-based, so Jupyter notebooks, Jupyter is a technology that doesn't have to be container-based, but most deployments are in containers. But most notebooks are Jupyter. There are Spark applications out there that use Zeppelin. Um, and These notebook containers run as a service account. This leads to a number of issues. We'll talk about those later in this presentation. What a data scientist is doing here, they're examining and scrubbing data, they're experimenting and visualizing data, they're creating toy models, and then they're launching large training jobs and automations. Distributed training is really the thing that gets most people excited about running these machine learning jobs within Kubernetes. They function very differently than these types of jobs on bare metal. Most of these follow what we call a job operator pattern. And these include the Spark jobs that you run in Kubernetes, TensorFlow jobs, PyTorch jobs, and there are dozens more as beta pieces of Kubeflow or other pieces out there. The way a job operator works is that a machine learning job custom resource of some type is submitted via kube control or other client tool to the Kubernetes API server. In Kubernetes, there's a machine learning job controller of some type that sees that custom resource that's been submitted, and it dynamically creates a set of control or parameter server pods and a set of worker pods. The worker pods retrieve and manipulate training data via APIs like CSI POSIX or S3 object storage or even HDFS. As the training job progresses, a model is created and logs are generated. When the job completes, all of the pods are torn down, so you don't have infrastructure staying around and taking up resources. One of the cool things you can do in this environment is because these patterns are almost always the same, whenever you submit one of these YAML files, you can always intercept that submission with an admission controller webhook. Even if you didn't build this type of job, and look at the job submission and do certain things with the YAML that was submitted to your job controller. There you can add various resources into the namespace that the job's going to run into. This can help really significantly ensuring that the proper secrets, config maps, or persistent volumes are created. Model serving is the final stage of the data science workflow that we were talking about. Model serving really doesn't typically require a lot of training data, and it's less data intense than the training side of things, but it does still require some challenges from the state perspective. The models that we created during distributed training must also be available for serving. So do we actually move this into production via some sort of pipeline or workflow engine? Or do we have some sort of distributed file system where both training and serving can get at that model container? We have to put our models in a container, and they're going to be serving responses to REST requests. But how do we actually put those model files in the container? Do we generate a new container for every set of model files? Or do we actually mount a universal model serving container to a particular model? These are the types of things that we want to think about. Unlike Hadoop, machine learning tools are really not unified around a single data access API. Different machine learning applications require different storage APIs. And that creates kind of a challenge for us. And this is the first of our challenges that we'll talk about. And that's data API availability. Since we're in Kubernetes, really the traditional way to think about talking to persistent storage is via POSIX. POSIX is great for a lot of things. CSI works really well in a lot of machine learning applications. It's great for speed, depending on the CSI driver that you select. It fits the Kubernetes model really well. But there can be issues if you use a CSI driver for something that's not a distributed file system. So CSI is not a panacea all the time when you want POSIX. You really have to have an underlying CSI driver that works well. Object storage, or S3, also fits in really well with machine learning. Kubernetes hasn't really had object storage catch up with POSIX in the CSI world yet, but that is something that's being worked on with the storage group. But from a machine learning perspective, a lot of the tools that we'll be using tend to work with object storage, and object storage is a very simple way to do things. It has a lot of performance and throughput issues, so pulling your training data in through object storage probably isn't the best way to do things. You could embed HDFS drivers in your pods. HDFS is a very fast, performant way to go after storage, but there's nothing built into the Kubernetes infrastructure to deal with it. To the final interfaces, NFS or database protocols, there could be many others. NFS, we do see several machine learning applications out there that do require specifically NFS. I wouldn't recommend it if you're designing things from scratch. It has some speed issues and some issues with stability and security. Database protocols, embedding those in containers. Anytime you have to embed drivers in containers, it bloats your containers and makes things more complicated. But there may be reasons you want to do that, HDFS being the canonical example. The key to really this part of the presentation is you need your data infrastructure to be able to support multiple protocols. Our second challenge is really how to deal with state that is used as libraries or various resources for the container. There are really two major schools of thought when you're putting together a notebook container or a training job container. One is to build a container for each task. So have a data scientist actually build the container especially for that training job or for that notebook. The second school of thought is really mounting a volume for the various libraries or assets into a common container. This lets you do things like store those libraries or asset files in a distributed file system, and lets you avoid creating hundreds and hundreds of containers. The container route does have a number of downsides. The number of containers that you build, your data scientist must be more skilled to some degree to create the containers. They have security issues that you really need to think about, and container management and storage. Volume mounting takes more time and planning. You have to create smarter containers. It probably requires a CSI provider with a distributed file system to do it. If you are going to go the route of creating a container for each job or notebook, I would recommend that you create pipelines or use a workflow engine like Argo to create those containers rather than create them by hand or via a recipe. Scripting it really breaks down fairly quickly. This challenge is the challenge of dealing with the gravity of training data. Data gravity is the idea that it's hard to move data around and that data naturally attracts compute closer to itself. There are a number of reasons why data gravity exists. The first is that it costs a lot of time and money to move some types of data. When you have hundreds of petabytes of sensor data, it's very costly to copy that information. You may have government regulations. I can't move data from here to there. It must reside within my borders. Finally, privacy concerns. I can't put this data in the data lake and use it for training because there are various privacy concerns that we have to deal with. Some tips to deal with data gravity. First, when data must live outside the cloud and within a corporate firewall, you need to choose between allowing external compute in the cloud to ingress into your data center or to create an on-prem Kubernetes environment. In the vast majority of cases, we see the on-prem solution tends to be the solution that works the best. There are specific instances where running compute in the cloud and going to on-prem works a little bit better, but performance, cost, security, legal reasons, usually you want to have an on-prem environment to deal with that data. In many cases, spinning up a quick Kubernetes solution in the cloud might be useful to handle the worries that IT has for data scientists rolling their own containers. In those cases, consider a shared cloud-based data lake for ephemeral data scientist Kubernetes environments to all share. In addition to the notion of data gravity, there's a closely related issue of data locality. The Hadoop world spent an extreme amount of time trying to ensure data locality and optimizing HDFS for this type of access. As network speeds have improved, what we found at MapR was that true data locality became less important with faster networks. In many cases, fast POSIX access to a quality distributed file system is really enough. Block storage, scheduler improvements, and custom schedulers may all make true data locality in Kubernetes and Kubeflow something that's reasonable for these machine learning frameworks in the future. But the Spark project has worked a lot on doing data locality in Kubernetes. But as it's not something that I would suggest you spend a lot of your time and energy on early on. There will be certainly use cases where it's important, but in most cases, actually having the data residing on a block device on that particular node is a very difficult thing to do, and you should approach it with caution. Our final and probably the most complex challenge is data security. I use the term data security broadly, and there are a lot of nuances we can't cover in this presentation, but I want to make sure you have just a few of the tips and just a way to think about data security and some of the reasons there's complexity. There are two main causes for these difficulties. One are the way namespaces work in Kubernetes, and the other is notebook service accounts. Namespaces and data don't really cooperate really well. Let's talk about three types of data. There's globally shared data, and that's data shared between multiple teams, users, and projects. There's team shared data, and that's data shared between team members and user data, and that's data for a single data scientist. When you combine that with the granularity and where the various Kubernetes storage artifacts live, like CSI, persistent volumes, and storage classes, and how they interact with secrets, it can be problematic. CSI uses secrets that contain the storage backend's credentials. And we need to actually have these secrets attached to persistent volumes or storage classes so that the driver can see those credentials and access storage securely. The problem is that if you're in a shared namespace, it's hard to protect those secrets from multiple users. So my tip is really to plan your namespaces and data owners very, very carefully. You really need to sketch out what PVs live where, who can access what in what namespace when you're setting up this infrastructure. The security implications are really important. The second area of data security that you have to pay attention to are team resources. Kubeflow has this profile namespace concept for individual users, and this is where notebooks run. But at the same time, most customers that we see actually think a lot about resource controls and resource quotas. One of the values of Kubernetes is that they can restrict a team, a data science team, to a certain number of CPUs and a certain amount of memory. And they want to enforce those quotas at a team level. That means you probably want to run your training jobs in the team namespaces. But that means that various things like persistent volumes and various resources need to be there in the team namespace as well as the user namespace. So my recommendation is to use webhooks or admission controllers, Istio and Jupyter Hub to create resources like volumes and storage classes in your profile namespaces for team volumes. And if you're going to run your training jobs in the team namespaces, have individual user volumes exist in that namespace, but make sure you spend a lot of time making sure the RBAC is secure. Finally, service accounts and data security. So data scientists live in notebooks. Notebooks live in containers, and those containers are launched by launch processes. And Istio routes the browser request to the right container. Because of the way all of this works, these containers don't run as the user themselves; they run as a service account. But inside of the container, the user needs to run training jobs as themselves. They need to talk to the data store as themselves, and this means they need credentials passed in. One of the big tips is, again, use webhooks or admission controllers to create secrets with these credentials, intercepting the notebook creation process, and creating these resources. Be very careful about what containers you allow users to exec into, because of the types of secrets that you'll want to mount into those containers. Thank you very much for listening to this presentation. There's some links in my email if you have questions.